All right, so where we left off, talking about unit weight and voids. So unit weight or density is the weight, in this case would be the weight of a material in a known volume. So maybe you have a certain pounds per cubic foot would be, basic density, basic unit weight. Unit weight, density, the same thing, tomato, tomato. You also have the voids content, which is the space in between the aggregate particles. And so you can actually figure out through ASTM C29, you can actually calculate, you can actually conduct the test to measure the unit weight of aggregate. You can also go from there and measure the voids content if you have the specific gravity number. And again, both of these numbers can be used whenever you're designing and batching and stuff. Unit weight is really important whenever you're batching. So you have your material, you put it in a known volume, such as a unit weight bucket, and then that's going to equal your unit weight because you weigh your material and then you know your volume. You can actually measure your volume based off of if you need to calibrate that unit weight bucket. Let's say you can actually put water in there, use a glass plate, get out all the air, and you can figure out, because we know the density of water at a certain temperature. So you can actually go and measure the temperature of the water and then weigh it, and you can actually figure out your unit weight pretty easy from that. The volume that's contained in that unit weight container, I should say. So when we talk about specific or we talk about unit weights, normally we start talking about specific gravity too. So this is extremely important, especially for designing a concrete mix. So specific gravity, what that is, it's actually a ratio between the density of a material to water. So in this case for aggregate, it's how much more dense is aggregate than water. Or, if you talk about cement, the specific gravity is 3.15. So 3 times, 3.15 times is the density compared to water. So it's more than 3 times as dense as water, cement is. So the specific gravity of aggregate it's the same thing as saying, if you have a volume of water and you have a volume of, we used cement just now, you also use aggregate, but they have the same volume, different weights. Okay, so like I said with cement's 3.15. That means if they're the exact same volume and you weigh water and then you weigh cement, the same volume, the cement's going to be 3.15 times larger in weight. So the specific gravity of aggregate, so you have 100 pounds of water and you have 260 pounds of aggregate. So what that's really trying to communicate is there's 260 pounds per the same volume and 100 pounds per the same volume of water. So density of aggregate divided by the density of water, 260 divided by 100 is 2.60. So that's actually a specific gravity of an aggregate. So whenever you say 2.62, 2.60, 2.74, that's actually what you're communicating when you say the specific gravity of aggregate is blank, because that's actually how much more dense, how much more does that aggregate weigh than water. It's also important to realize that moisture plays a huge role in figuring out the specific gravity. So you can actually figure out the specific gravity when it's at SSD, and that's what we design concrete with. You can also look at when the specific gravity is at dry. So both matter, both change the weight. Obviously, you're going to be a little heavier when there's water in the rock too. So just kind of be aware of that. We can run specific gravity and absorption. We'll have a lab over that where we actually let it saturate for 24 hours. We dry it off with a towel, and then we put it on a bucket and we put it back in the submerged weight. And we can, weigh out the sample before when it's dry on the surface, and then we can weigh it when it's actually submerged in the water, and we can figure out our actual specific gravity from that. We can also figure out with this measurement here, this step 2, we can also take it in and dry out our aggregate, put it in the oven, and come up with our absorption. So there's, basic equations depending on what you want to know. Bulk specific gravity, SSD, is here. That's what we normally use for concrete. And then our absorption value, which is here. So again, this is kind of where the variables are. We also do specific gravity of fine aggregate. It's not very fun because you have a flask and you have to make sure that the aggregate's right at specific, right at SSD. If you want to measure the bulk specific gravity SSD, it's kind of a pain. But in essence, you fill up your flask full of water. You make sure your fine aggregate's well above the free, has free water in it, so it's well above the SSD. If you're trying to measure for SSD, go in. A lot of times you'll take a blow dryer or a fan, and you continuously you'll mix the sample and let it dry out, and you'll do it until that sample finally doesn't mold, isn't able to stick together. And it's right when that thing isn't ready to stick together, like right at the very, very, very first time it doesn't stick together, before it dries out too much, then you go and you put it in this flask and you see how much the elevation, the actual temp, the actual water changes, and that measures your specific gravity. So just kind of be aware of how that's done. So your unit weight and your specific gravity of your aggregates is actually measured here. So for this is just common numbers. So for specific gravity, for coarse aggregate, depending on your geology, or fine aggregate, depending on your geology, it's here. You can also talk about unit weight. And again, you can kind of look, these are just general numbers. They may not be exact for what your aggregate source is. You can also talk about crushed particles. So this is uncrushed, like river gravel, and then you can take it through a crusher and actually crush the particles, so you can provide more interparticle friction, more interparticle interaction, and it's a lot more important, especially for asphalt, to do this. But it will improve the strength of your concrete too, by not having just a bunch of really soft particles. So it's important. That might help workability, but when it comes to the strength, it'll actually reduce it quite a bit. So just kind of be aware of that. You can actually go through OHDL. Oklahoma has a standard where you can go through and actually check out the crushed particles for, say, coarse aggregate. You can figure out how many crushed faces there are, like you have here, where there's 1 crushed face, 0 crushed face, and then more than 2. And you can actually calculate that. For flat and elongated for your coarse aggregate, you can do pretty much the same thing. We can actually take it off this measurement device here, and you can measure the ratio to figure out if you have flat particles or elongated particles, or if they're both flat and elongated. So you can do both, and there's some specs out there for flat, or flat and elongated, or just elongated. So kind of be aware of that. So this is kind of an illustration of what that's all about. Whether if it's a perfect cube or perfect sphere, you're going to have, kind of symmetrical dimensions. And as you get flat, flat just means that, the smallest dimension is a lot more than the top one. So a lot more, you know, this is like a 1:5 ratio. This would be a 1:10 ratio for flat. So if you want to do flat and elongated, you would actually have to compare, you know, flat and elongated number. And then just for elongation, you just compare your elongation and your to how long it is compared to how thick it is and stuff, your second dimension. So all right, so abrasion, again, we talked about the resistance to particles breaking. So you pretty much you put a known gradation into this big drum with a bunch of steel spheres, and you go for 500 revolutions. These steel spheres are supposed to break up the rock, and depending on, you look at your gradation afterwards, and if it changes more than 25 to maybe 55%, that's the maximum range you're allowed. So it just depends on what standard it is. It might only say 25. It may even be up to 55, depending on what you know, what the standard says. So again, for illustrations, a known sieve size, you put it through this LA abrasion machine, and it comes out the other side after 500 revolutions with these still sphere balls. And you're going to have a breakdown of gradation. And depending on how much it is kind of talks about your loss. Impurities, so when you talk about clays and fines, like you see here with these mason jars I've already talked about in lab, you can take like a half of sand, and then the rest is water, and you can shake it up. And as it settles, you can figure out how much maybe clay or fines, because they'll separate depending on the density of them. The lighter ones will go up, the heavier ones will go down. You can do the same thing with your coarse aggregate. So how well you can actually see your coarse aggregate after you shake it up. As it gets dirtier and dirtier, that means you have more and more fines. So that kind of helps for, you know, if you're troubleshooting in the field. You know, for slate, chert, coal, lignite, they actually have their own standard, and you can actually look up that standard to figure out and measure it. Silica and dolomite impurities, maybe for ASR or ACR in concrete, so alkali silica reaction or alkali carbonate reaction, and that actually can crack your concrete whenever the alkalis in your cement react with the silica or the carbonate and the limestone or dolomite, and it can, or even your silica sand, and it can react with the impurities in there and cause micro cracking, internal cracking everywhere. And, you know, you have to redo your concrete a lot of times. We also talk about if you have high chlorides in your actual aggregate, it promotes corrosion, so you really don't want that. We talk about freeze-thaw. This is about, again, when water goes into your aggregate and it freezes and it unthaws, and over time, if there's a bunch of cycles of freezing and unthawing, your concrete's going to crack in a certain shape, and that's not good for the concrete. So this test, to test if you have freeze-thaw durability issues, usually takes somewhere between 6 and 8 weeks. And really, some people say it's a little too harsh for compared to field performance, but I think it'll give you, if your aggregates, your coarse aggregates pass this, you know, this freezing and thawing test, then I think they'll be just fine. So you can kind of see here's decracking. A lot of times you'll see it in areas that have drainage, where the drainage is, or on the edges of a slab where things are sawed out. Like this is a parking lot up in Kansas. And so over here in the middle of that panel, there's no really cracking, but on the outsides it's really tight, dark cracking, and it's a bunch of chipping that comes up too with it. So how this freeze-thaw test works, ASTM C666, It's 300 cycles. AASHTO has one for 350. They're the same test, but in essence, you make some beams with, in this case, for the aggregate that you're trying to test. You make sure the mix design is going to be adequate, has adequate air and everything. It's going to perform well. You run it through this 666, this with these freezing and thawing cycles that occur, and then you calculate the durability factor. So you see how well over time that the modulus, the dynamic modulus, how well it works. So you make an impact, and you have a sensor here, and you see how well that's going to perform over time. You also have sulfate soundness. So whether it's sodium sulfate or magnesium sulfate, what it really looks at is how well the salts are going to attack your aggregate. So this takes about a week to run. Doesn't always reflect what I'd say durability. Some people talk about how it's, reflects freeze-thaw performance. I don't agree. It's more of like your sulfates and how well the aggregate's going to have issues. So you prepare your sample with a specific gradation. You take and you run 5 cycles of 6 hours soaked in solution and 4 hours of it being air dry. And you do go through all these cycles, and then you re-sieve it and you calculate your loss, and that kind of figures it out. So I talked about a lot of different testing today. Usually you're going to have a report. We're going to be writing an aggregate report, a full one. If you want more of like a more of like a summarized aggregate report, sometimes people will provide those. Sometimes they may have 2 or 3 or 4 different pages of testing. It just depends, and we'll write a full aggregate report. So again, aggregate reports, they're going to provide the test results. Any lab report is supposed to provide test results, what tests they actually ran, and what they'll look at. So for most aggregate test results, you're going to have gradation, what your sieve analysis was. They're usually going to run specific gravity and absorption on it. And they're going to a lot of times run unit weight, and they'll have all that. It may be just 1 page, may just be 1 page of results. It may be a bunch of pages of results. It just depends on who the lab is and who's preparing it. A lot of times you may not receive the transmittal letter or the cover page, but you may just receive, the 1 to 3 page body of the report. But it's important to realize that a lot of times it's actually a full report. You just don't know it. So with that, I will be done for today. Have a great day.